All right, today we're going to do Unit 5, Lesson 3, representing exponential growth. So we're going to explore exponential growth to some various situations. So we need to first rewrite each of these expressions as the power of 2. So for the first one, we have 2 to the power of 3. So that represents having 3 2's being multiplied. So 2 times 2 times 2. So I have 3 of those. And then 2 to the power of 4 is 2 times 2 times 2 times 2. So I have 4 of those. When I'm multiplying those by each other, I have 2 to the power of 3 times 2 to the power of 4. Well, I can just add those together. 3 plus 4 equals 7. So it's 2 to the power of 7. So 2 to the power of 3 times 2 to the power of 4, we can add the exponent because we're essentially adding the number of 2's that we're multiplying by itself, and we get 2 to the power of 7. So if I have 2 to the power of 5 times 2 to the power of 1, I'm going to add those together. So 2 to the power of 5 plus 1, so 5 plus 1 equals 6, so it's 2 to the power of 6. Now if I'm dividing them, it's going to be the opposite of multiplying them. So I'm going to have 10 2's. So 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all being multiplied by each other, divided by 2 to the power of 7. 1, 2, 3, 4, 5, 6, 7. And so instead of adding those exponents, I'm going to see how many I have left. So you can cancel them out because 2 divided by 2 is 1. So the ones that cancel each other out will just be 1. And I'm left with 3, which is the same as 10 minus 7. So this is going to give us 2 to the power of 3. Also, if I have 2 to the power of 9 divided by 2 to the power of 1, 9 minus 1 is 8. So that's going to give me 2 to the power of 8. All right. So we're going to look at this table. We have our input as x on the top, and then our output is 3 to the power of x. So when our output is 3 being raised to the power of x, 3 to the power of 4 is 81. 3 to the power of 3 is 27. 3 to the power of 2 is
a number.
Wait,
power 9.
9? Okay.
3 to the power of 1. 3. What about 3 to the power of 0?
0.
No.
3. 1.
If I have 1. So it's still going to be 1 because I'm raising something to the power of 1. Oh. Okay. So let's look at these equations. If I want to multiply something to the power 9 to the power of something by 9 to the power of 7, what does that need to be in order for me to get 9 to the power of 7? What is the only thing we can multiply by 9 to the power of 7 and get 9 to the power of 7? 1. So I need this 9 to the power of something to be 1. So that needs to be 0. So 9 to the power of 0 is going to give me 1. And then 1 times 9 to the power of 7 is 9 to the power of 7. Through division, if I have 9 to the power of 12 divided by 9 to the power of something, what does that question mark need to be in order for me to get 9 to the power of 12?
0.
0. Okay. So what's 5 to the power of 0?
1.
1. What's 2 to the power of 0?
1.
Because anything raised to the power of 0 is 1.
Oh, I need that. I wasn't writing that down.
Where's my record box?
Yep.
All right, so let's look at this situation. We have a biology lab that has 500 bacteria reproducing by splitting. So every hour, one bacteria is going to split into 2 bacteria. So we need to write an expression to show how to find the number of bacteria after each hour listed. So if I start out, initially I have 500 bacteria. After the first hour, what am I going to do to find out how many bacteria I will have then? We're going to multiply by 2. So 500 times 2 will give me that first hour's amount of bacteria. What about after the second hour? Well, I'm going to have 500, and I'm going to multiply that by 2, and then multiply it by 2 again. For the third hour, I'm going to have 500 bacteria that I initially started out with, and then I'm going to multiply it by 2 twice, and then one more time to double it a third time. What is a faster way that I could write that?
500 times 2 to the power of
Right, 500 times 2 to the power of 3. So then when I do that 6 times, if I want to look at the 6th hour, I can just change that to 500 times 2 to the power of 6.
What if that's not easier?
So I need to write that equation using n to represent the number of bacteria that I have total, and t is the number of hours that I am looking at. So I'm going to use the same thing we did each hour. So n equals 500 times 2, because it's doubling, raised to t, the number of hours that I have. Okay. So what if I want to use and figure out when n is 0? How many bacteria will that tell me that I have? Well, if I have 500 times 2 to the power of 0, 2 to the power of 0 is
I forgot to make
1.
it not tiny.
So 500 times 2 to the power of 0. 2 to the power of 0 is 1. 1 times 500 is 500. So that tells me the initial amount of bacteria that I'm starting out with, or the number of bacteria I have at hour 0.
No.
All right, in a different biology lab, we have a population of single-cell parasites that are also reproducing hourly. So our equation here is P equals 100 times 3 to the power of T. So what does the 100 represent in this equation? The 500 up here represented the initial amount of bacteria that we started out with at hour 0. So what's the 100 represent?
What?
The numbers of bacteria?
The initial amount of single-cell parasites, because now we're looking at parasites. Okay, so it's how many parasites we have at hour 0. What does the 3 represent?
It's tripling.
That it's tripling. So now we know that the parasites are splitting into 3 every hour instead of splitting into 2 like they did before. So the 2 and the 3 represent a growth factor. All right, so this next slide we're going to look at is how we're going to graph it. So we're just going to graph both of those expressions that we just had. I already have them graphed up here. So our slide is asking you where we can see the 500 and the 2. So for the first equation, 500 represented the initial amount of bacteria that we had. And you can see that on the graph where it crosses the y-axis. So our y-intercept is where we can see 500. And it tells us that we have 500 bacteria at hour 0. On the other equation, we can see the 100 in the same spot. We can see that it is also the y-intercept, and it is crossing the y-axis at 0, 100. So we have 100 bacteria or single-cell parasites initially. The 2 and the 3 are our growth factors. We can't see those as clearly on the graph, but you can see because it is doubling every time. So every hour that passes, you can see that the bacteria double on the red line. So it is doubling every hour. And then on the blue line, you can see that every time it is tripling as you increase it. So for 1, every time the x value increases 1, the y value increases by 3. Okay? So going back here. All right, so on the graph, we can see each number that appears by the 500 is the y-intercept at hour 0, and the 2 is your growth factor that we can see that it is doubling every time the t value increases by 1. And t in this expression is your x value, so it's the same thing you see on your x-axis. On the graph of p, the 100 is your y-intercept at 0, and 3, you can see it tripling every time the hour increases on your x-axis.
No way. June.
All right, so I want to make sure that you understand the parts. So we're going to look at this situation, and you have the graph. So 1,000 times 2 to the power of t represents a fish population t years. So looking at the graph and the equation, what was the fish population when the scientists first measured it?
2,000. No, 1,500.
1,000. We can see it because it is the y-intercept on the graph, and it is the initial amount that you see in your equation. So 1,000 is the initial amount, and we can see it on the graph as the y-intercept, or the amount of fish that we have at 0 years. How is the fish population changing from year to year? We can see that in the equation because we're multiplying by 2 every time. On the graph, you can see that it has 1,000. After the first year, it increases to 2,000. The second year, we have 4,000. The third year, we have 8,000. So you can see that it is doubling every year. And then number 4, how does the expression 1,000 times 2 to the power of t represent the fish population after t years? The 1,000 is the initial value and the amount of fish that you have at hour 0, or year 0 here. And 2 represents that it is doubling for every year that you're observing the fish population. So it's just important that you know that that first number represents the initial amount that you have, and what it's being multiplied by is your growth factor. So it's going to tell you if it's doubling or tripling or increasing and being multiplied by 4 or 5 or 10 or whatever that value is that you're growing the function by every year.
You want a video?